Let's work a constant acceleration example problem. So here we have a situation where they tell us in the fastest measured tennis serve, the ball is going to leave the racket at 73.14 meters per second. So in my mind, as I'm reading, I'm just trying to kind of make note of what information they give us. So this is AV, right? That gives me information about the speed at some point in this scenario. Then they tell us a serve tennis ball is typically in contact with the racket for 30, and that ms, that's milliseconds. I'm going to highlight that. So that's going to be a time. I'll put just a little kind of T below it. Another thing, as soon as I see milliseconds, I'm thinking I want to convert that into seconds. So remember, anytime we're doing our calculations, we always want to be thinking about getting everything into those base units. So if the quantities are given to us in anything other than kilograms, meters, seconds, we want to convert those back to those base units. So for this one, this is a conversion you should know. So 1 millisecond is equal to 10 to the negative third seconds. So I'll keep that in mind as I apply that number throughout the problem. So I got a little distracted there with the milliseconds, but it says, so the ball is typically in contact with a racket for 30 milliseconds, and then it starts from rest. So that's another V information, right? And it starts, so I'm going to call that V naught, starts from rest. That means that's equal to 0. Then it says assume constant acceleration. So that also is important. So sometimes one of the most difficult parts about this course, especially as we get later into the semester and we mix up all different kinds of problems, is identifying what type of problem is it, right? Is it a constant acceleration or is it an energy problem? And so early on, we don't have as many types to choose from, but still we want to kind of think about that. In this problem, they tell us that it's constant acceleration, so they take that decision making away from us. But if they didn't say it explicitly, we could think about things in the problem statement that say, you know, it's changing speed at a constant rate, so either slowing down or speeding up at a constant rate, and that would be a clue to us that this would be a constant acceleration problem. All right, so they tell us it is, so we know it is. As soon as we know it's constant acceleration, I should be thinking I want to make an interval. So I'm going to make an interval. So even if I don't really know what is going into that interval, I can start with an interval, right? And then apply the context of the problem to our interval. So an interval always is going to have a start and an end. So I want to think about in our problem, what is the start and what is the end? And so what's kind of going on in between. And so in this case, where they're telling us that the ball is going to start from rest and then it's going to leave the racket. So our interval here is that duration of time while the ball is actually in contact with the racket. So it's a really small amount of time, right? But it is an interval. It is a measurable amount of time. So at the end, so I'm just going to put a little note here, right? This is when the ball leaves the racket, and I'll just say this over here. This would be first contact to put some context in the problem. So I have an interval because it's just this duration of time with the racket. We're going to assume this is just one directional motion. So I'm going to put a positive direction here. We have always our 6 variables. So I'm going to always have a starting position. I'm going to have an ending position. I'm going to have a starting velocity. I'm going to have an ending velocity. I'm going to have an acceleration across our interval here. And then I'm going to have some time that is the duration of the interval itself. And so I always have those 6 variables. I do like to say what's going on in the interval. So if we think about this situation, they're going to tell us that we're starting from rest. So I'm going to go ahead and put that in here. So I know I'm starting from rest. And then we're going to leave the ball, or the ball is going to leave the racket 73.14 meters per second. So it's speeding up, right? So I can make a little, just make a quick little, throw a couple of vectors in there. So that helps just communicate that we are speeding up. One of the things you want to do with your picture is be able to come back, and if you look at this, say next week, you should be able to look at your picture and just really quickly know what the problem was about, right? So you should be able to look at the picture and say, oh, something was speeding up. It started at rest. It had some speed when it was leaving. And as we put more information in, you should also be able to just kind of from your picture tell what we're trying to solve for. All right, so we have our, I'm going to just make a note here. So we have this information in our diagram and defined. They also told us that T, so I'm gonna go ahead and plug T in here as well. And remember, we need to make that little adjustment here. So this is 30 milliseconds, but that 30 milliseconds, I'm just gonna write it like this, is 30 times 10 to the negative third seconds. We do not know what the acceleration is, so they just tell us that it's constant, and we do not know, the distance that it covers while it's in contact with a rocket. Okay, so we can put in, we oftentimes will put a 0 here, so we can set our 0 point for position. So we have two things that we don't know, and if I had actually read the questions, I think these are the two things we're going to find. So so what's the ball's acceleration? So this is one of the things I want to find. And then how far will the ball travel while in contact with the rocket? Okay, so we're looking for that X, that final position, and we're looking for our acceleration here. So once we have this diagram, right, we've done a lot of work putting this diagram together and defining all of our variables. We have our coordinate system up here. Once we've done this and set this up, then we're going to go and grab one of our equations. And I just added those little equations here. These equations are on your equation sheet. And from this point on, this is just algebra. We're literally just plugging into these equations. This should go really, really quickly if we set up all of these pieces here. So let's start with our acceleration. So if I want to solve for acceleration, we want to pick one of these equations, right? So we definitely want an equation that has acceleration in it. And so if you look at those, they all have acceleration in them. The other thing that we don't know is this position. So I don't want to pick an equation that has the thing I want and another thing missing. So if I look at this equation, so this equation has my V final, which we know, it has my V initial, and it has a T. So it has everything that we know, everything that we want, which is the acceleration, and all of the other pieces of that equation are things that were given to us. So that's going to be an ideal equation for us to pick to solve for acceleration. We would not want to pick this one here. So yes, this has our acceleration, but if I run down that list, right, I don't know this here. So this equation, if I pick that second equation, I would have two unknowns. So that's not going to be helpful. Same thing would be true here. Here's my acceleration, but then I don't know that X either. So usually there's an equation that will work. So sometimes depending on what information you have, or maybe you only have 3 pieces of information, you may have to do go through multiple equations. But if we can do it in one shot, of course, we want to do that. We want to be as efficient as possible. So for A, we're going to use that equation. You do need to show this equation, right, without plugging anything in. So I want to see this equation like this. So even if some of that stuff in there is 0, we're going to show it like this. This is what we call the starting equation. So we're going to show it with just the variables like this. Then our next step is just plugging in and solving, or rearranging whatever we have, whatever I have to do to get our final answer. So I'm going to run through here. So this I know, just real quick again, this I know, this is 0. This is the thing I'm looking for, and this I know, right? So this is a great option for us. I always like to rearrange before I plug things in. So this is just going to be Vx over T. And at that point, then I can go ahead and plug my information in. We have 73.14 meters per second over that 30 times 10 to the negative third times 10 to the negative third seconds. And so my acceleration here is just going to be 2,440 meters per second, and that should be meters per second squared. If we have our units in there, we can do that quick check, right? So I've got V up top that has meters per second, and I got a time on the bottom. So I end up with meters per second squared, which is a unit for acceleration. So we are in good shape. That all is consistent with what we want. Okay, so that was A. B was how far does the rocket travel? So now I'm just looking for this position. Again, I go back to my equations. So first equation doesn't have position in it, so definitely not going to use that. So we have our other two options. We have A and B here. Both of those have the variable that we're interested in. And now that we know acceleration, we know all of the other variables. So I actually could pick either of those to work with. I'm going to just pick A because that's the one I'll use. You could actually do both of them and solve and show that you can get the same answer either way. So again, I'm going to write this out entirely first. So we got 1/2 AT squared. The thing I'm solving for, I always like to highlight. Then we can go through. So one of the reasons I like to pick this one, if we have a case where my initial position and velocity are 0, is because both of those terms go to 0. So then we are just left with our final position of this interval is just 1/2 AX t squared. I can plug in my acceleration that we just calculated. So this is 2,440 meters per second squared, and then multiply by our time, which was 30, not 3, 30 times 10 to the negative third seconds. And then I need to remember to square that piece there. And so when we do all of that, we end up with 1.10 meters. And that is going to be how the distance over which that ball, the tennis ball, is in contact with the racket there. Okay, so in this problem, this is what I would consider just kind of a classic basic constant acceleration problem. There's not anything tricky in here yet. They just give us one scenario. We only have one interval. So if this was a problem on an exam, I just want to run through real quickly kind of how this would get scored, right? So this diagram piece up here with all of the variables being defined, this is always at least 30% of the points for the problem. So I'm looking for start and end of your interval, all 6 variables defined. Do you have your coordinate system here? Then starting equations. So these would probably be 10, 15%. If there's any more complex calculation pieces, so sometimes we'll need to do some simultaneous equations, or if we have multiple intervals, those will take up some of the points. But in pretty much every problem that we do this semester, 30-ish% of the points are going to come just from that diagram and defining your variables that we're working with. So you want to get in a good habit of starting with that. Again, when we're working with constant acceleration, once we have that diagram and we have our 6 variables defined, the rest of it is just picking equation and kind of plugging and chugging, right? So getting that diagram set up well, defining your variables is super important to help you be really efficient with your problem solving.